on this computer. Okay, it's recording now.
Okay, thanks.
I think you can go ahead.
All right. Okay, so today I'll be talking about stabilizer states and magic. So the term magic is a technical term that I'll define. And I will give examples from qubits to quantum field theory and holography, and that hopefully will explain why someone like me with a background in holography ended up in this topic. So here's a summary of what I'm going to say in case you lose your interest halfway when we go through the details. The plan is to talk about or review what was called stabilizer states. So in simple terms, oops, what is my, okay. In simple terms, these are entangled states that are easy to simulate classically. So usually we say that quantum computers are going to be more powerful than classical computers because we have the power of entanglement. But it's incorrect to think that every time you have entangled states, you have an advantage over classical computers. Stabilizer states are famously a class of entangled states that are easy to simulate classically. So that's intuition. And they play an important role in error correction codes, quantum error correction codes, topological quantum computing, and tensor network models of holography. So a lot of this literature that you might be familiar with uses stabilizer states. So non-stabilizer states that give us advantage over classical computers are not really discussed or used in any of these constructions. So which suggests that a lot of this is easy to simulate classically. So quantum is not an advantage or significant advantage. So what are magic states? Magic states are the opposite, anything that's non-stabilizer. So it's sort of a resource that allows us to go beyond something that could be done efficiently classically. So it's like, it gives us some advantage quantum mechanically. So we'll go through that. The point that I particularly care a lot about is the observation that ground states of CFDs seem to, this is suggested by a bunch of calculations done in this paper from last year that was published this year. No, last year, sorry, 2022, 2022, by Brian Swingle and collaborators, that argues that ground state of CFDs have magic at all scales. So in particular, this implies that if we are to construct more realistic models of holography based on quantum error correction codes, we'll have to squeeze in some sort of magic gates. I'll explain what magic gates are, more magic states. So this is sort of the summary of the talk. This is where we're going to go, and that's the plan of the talk. I don't know why this empty page keeps popping up. All right. Is the plan clear? Please interrupt me at any point. There's no point in me running and going ahead with a bunch of definitions that no one cares about. So feel free to ask questions at any point. So here are some definitions. I'll try to go through them very quickly. Of course, so almost all the discussions that I'm going to have in the beginning of the first half of the talk are going to be explaining what stabilizer states are, reviewing what stabilizer states are, and it's easiest to explain this using qubits. So I'll be talking about n qubits, right? So in particular, we're going to be thinking about unitaries, local unitaries, right? So unitaries on the first qubit, tensor unitaries on the second qubit, tensor unitaries on the third qubit, and so on and so forth. There is a subgroup of unitaries on n qubits that's called the Pauli group. This Pauli group is generated using the Pauli operators. So you have the identity, Pauli X, Pauli Y, Pauli Z, and these guys multiplied by plus minus 1. And this is the Pauli group for one particular qubit. Note that it's discrete, right? It's a discrete subset of the unitaries. Unitaries are continuous. And then you could take this to tensor n. So this is the Pauli group of n qubits. I'll denote it using Gn. Of course, it has a center. Sorry, yes?
Nima,
Yes.
why, as for why, so you use Okay, y is not a poly y. Why you wrote down as 1 minus 1, or you miss the I, or you purposely use
Oh no, I purposely multiply this with I.
Okay. Okay.
Yeah, sorry.
It's actually
The
fine.
z should have a minus 1 or not. The z is.
Yes,
have a
thank
minus
you.
one.
Typo. Yes.
Mhm.
Thanks so much.
Mhm.
Yeah, so this is, I intentionally keep them real. Yeah, so let's not worry much about representation. The point is that all that you need to know about this subgroup of the unitary group is that members of this subgroup square to either identity or minus identity. If so, the rule is like this: if the one sequence of these guys has an even number of y's, it's a Hermitian operator. If it has an odd number of y's, it's anti-Hermitian. So it's either Hermitian or anti-Hermitian. Another thing that's neat about this subgroup is that the elements of this subgroup either commute or anti-commute. So these rules are important because they help us construct error correction codes that are called stabilizer codes. And I'll go over the construction. Is the definition of Pauli group clear? So it's always discrete. That's important. And the fact is discrete is going to be one of the reasons that they're going to be efficiently simulatable using classical computers, as opposed to generic quantum states, which are parameterized using continuous parameters. These are parameterized using discrete parameters. All right, so there's another piece of jargon that is important to know. It's called the Clifford group. So what is the Clifford group? These are the set of unitaries that send members of the Pauli group to itself. So these are the members of the unitary group that preserve the Pauli group. Okay, I mean, mathematically, it means that this is a normalizer of the subgroup Pauli group. That's what it's called. But the important thing if you want to know, have an intuition as what this group is basically the group that is generated using 3 generators. First of all, it's also discrete. It's generated using 3 generators. One of them is Hadamard, right? It's a thing that goes from the computational 0-1 basis to plus-minus basis. The other guy is a phase operator, which is one identity diagonal, right? It just adds a phase. And then the last one, so these are single qubit gates. And then the last one is a C0 gate. So it's a 2 qubit gate and it does C0, right? So this, any circuit that only has these 3 gates is called a Clifford circuit. And as an operator, it's these guys generate a group on the multiplication. It's called a Clifford group. Technically, it could be also defined as a normalizer of the Pauli group. So what's important is this, that again, let me just say what the statement is at the end of the day. The point is that these 3 guys, C0 generates entanglement. This creates superpositions. Hadamard creates superposition. P adds phases. So if you logically want to think about what these gates do, they actually give us a bunch of things that we do not have in the classical world, like superpositions, phases, and entanglement. However, they don't give us an advantage over quantum computers. So the Clifford circuits that only have Clifford gates are called stabilizer circuits, or sometimes called Clifford circuits, depending on how you want to call them. So stabilizer circuit only has stabilizer gates. These are called stabilizer gates. That's another terminology for us. So importantly, these guys, of course, are not universal, meaning that there are a lot of quantum gates that are not generated like this, because this subgroup is discrete, whereas the group of quantum gates is continuous, right? And it's known that all you need to do to get something universal is to add one extra gate that's called T. It's usually the standard terminology that adds a phase which is e to the power of I pi over 4. In fact, I could have chosen any number that is not 1 or I or minus 1. It's like I could have chosen any phase, any random phase, e to the power of pi over 3 or something. That's the only thing that matters, right? So all you need is this T gate. Usually it's taken to be the T gate because it's easier to work with. All right, so definitions. Stabilizer circuits only have these, are circuits that only have these 3 gates. So we don't allow T gates. And stabilizer states are all the states you could get by acting with these gates on 0 tensor n, right? So some Clifford group member acting on 0 tensor. So as I said, stabilizer gates are not universal, even though they make superpositions, phase shifts, and entangled states. Many quantum protocols use only stabilizer states. For example, quantum teleportation, quantum key distribution, the famous BB84 protocol, they only use these states, which means that, as we're going to see, which means that all of these protocols that use entanglement are actually could be done on classical computers efficiently. So they don't buy us some extra power. So just to know just to have in mind what I mean when I say that these are not universal, by acting with this H Hadamard phase gate and well, on a single qubit, because if I have a single qubit, I don't have C naught, I can't act with C naught. All I get is 6 states. I can't get any arbitrary single qubit gate, state, just because these guys are discrete, right? I can only get this 6 states and nothing in between. It's a discrete set of states I get. Stabilizer states can be simulated efficiently using classical computers, even though they're entangled. So this is some statement that we're going to come back to. All right, so this is all the definitions for stabilizer states I wanted to go over. The punchline we're going to see is that entanglement doesn't, every time you have entanglement, it doesn't mean that you have an advantage over classical computers. Is this clear? Are there any questions?
Just what do you mean by simulate a state? It means that you can do the evolution with some Hamiltonian with those gates. So what do you mean
Meaning
by
that I can write down a classical algorithm. So these are matrix multiplication or diagonalizing some Hamiltonian, some 2 to the power of n times 2 to the power of n. You know, so this state is found by minimizing, say it's the ground state of some Hamiltonian. So there's a polynomial, there's an classical algorithm that finds this state for you using only polynomial resources, or the time to achieve to prepare this state takes as scales like polynomial with the number of sites.
Okay.
All right. So this is one motivation to study stabilizer states, but this is a motivation from the point of view of technology and quantum computers and you know, advantage over in the world of computation.
Nima?
Yes.
I have a question. So, what is the size of the Hilbert space for the stabilizer state when we increase n?
So they do not span a Hilbert space because they're discrete.
Mm-hmm.
Right? So it's not like you do not allow, so the number of them is finite. For example, here in one qubit system, there are just 6 states. It's not a subspace.
Mm-hmm.
Yeah.
I see. Mm-hmm.
Okay. Now, so this is one motivation to study these states. It's from the perspective of computation, but these states actually have a deeper connection to other things that we care about. There, one statement that's important is this. Almost all, or said differently, to be more fair, the vast majority of quantum error correction codes that we know are constructed using are called stabilizer codes, and they involve only stabilizer states. So this is one other motivation. If you're interested in quantum error correction, you naturally, almost all of the codes that we know are of this type. So stabilizer codes, what are they? I'm going to give the mathematical definition. So again, we start with the Pauli group. So these are just sigma x, sigma y, sigma z with a funky normalization that I don't put the I in the sigma y. And I'm going to consider an abelian subgroup of this that I call S. This subgroup is called the stabilizer subgroup. And the stabilizer states, this is an equivalent definition. Well, I haven't proven to you that it's equivalent, but it turns out to be an equivalent definition for stabilizer states. These are states that are invariant over the action, under the action of this abelian subgroup. So this, let's just take this as another definition of stabilizer states. So I pick an abelian subgroup, and all the states that are invariant under the action of all the members of this abelian subgroup, so are called stabilizer states. So for example, I pick some abelian subgroup. M is a member of this subgroup, so an element of this subgroup, and if it's acting on some vector, it leaves it invariant for all members of S, elements of S, then I call this the stabilizer state. If my abelian subgroup has n minus k generators, then the invariant subspace, which is now a subspace, right? Because I can superpose them. The superposition also will be invariant, is 2 to the power of k dimensional. So it's a k qubit subspace. So M1 to Mn minus k are the generators of S. And these guys are gonna be the check operators in the quantum error correction codes. So in the language of quantum error correction codes, the invariant states under the stabilizer subgroup are going to be the code subspace. And if I have a total of n physical qubits and n minus k generators for this abelian subgroup, my code subspace will contain k logical qubits. Is the statement clear? Okay, so I'm going to quickly explain how the error correction works. Let's say n is some error. I should call it E. Well, I think yeah. Well, let's call it n because so both the notation n or m or ea, they both mean errors, right? But here by error n, I mean it's a member of the Pauli group, right? So we said that the members of the Pauli group have this property that they either commute or anti-commute. So n either commutes with all members of the abelian subgroup or anti-commutes. If it anti-commutes, so consider the first the case that it anti-commutes. So n as an error acts on your encoded state psi, and you could use mk, an element of your abelian subgroup, to check whether the error has acted or not. Because when mk acts on this corrupt state, you'll get a minus sign. If the error hadn't occurred, of course, you would not get a minus sign. So you could use the elements of the abelian subgroup to check whether an error occurred. And of course, if you realize that there was an error that occurred, all you need to do is that you have to apply the dagger of the error. So you have to be able to figure out what the error was, and then there's always a way. The whole content of the error correction code is a chart to tell you which error occurred based on these signs, right? So you get a corrupt state and act on it with all the check operators. These are the generators of your abelian subgroup, and you get a collection of plus and minuses, right? These are the syndromes. And there's a chart that tells you based on the syndrome what error occurred, and then you apply the dagger of it and correct your state. So this is called a recovery map. So we said errors either commute or anti-commute with your generators. So this was the case that the anti-commute.
Lima,
Yes.
So here, okay, are you considering a particular type of arrows? So n in general, I would say generically n can be anything, right? Since n represents arrow. So
Yeah.
why here you just consider?
So the nice thing about error correction codes is that all you need to show is that okay, there's a statement that I've not told you yet, which is, so if there is a set of operators in the Pauli subgroup that you could correct, a set of errors in the Pauli subgroup you could correct, you could also correct any superposition of them.
That is fine, but how about some operators that is not based within this algebra at all? It's not in this Pauli group at all.
That's what I'm saying. So if you superpose, the Pauli group is discrete. So if you superpose them, you immediately leave the subgroup. Like, for example, think about Shor code, right? One of the simplest codes in quantum information theory. The way we correct the Shor code is that we first make sure we could correct Z errors.
Oh,
then we make sure we can correct X errors,
mm-hmm.
and then comes out of the construction all the superpositions of them and also multiplication of them, which is the Y errors, right? But the logical construction of the error goes through making sure that you could correct to orthogonal set of errors.
Mm-hmm. Okay.
Yeah, but I mean, I understand that I'm sort of hiding all of this complexity, but I actually had a slide here to explain the necessary sufficient condition for error correction called the nil-Laflamme, but then I just removed it because I wanted to get to the CFT stuff. So this error, either if it's a Pauli error, either anti-commutes or commutes with your check operators. So if it anti-commutes, we say it's correctable. Now, if it commutes, it's correctable only if n is actually a check operator itself, which means that it doesn't change your state, which means that you don't need to correct it, right? So any error that commutes with all your check operators is something that you cannot correct. Of course, there won't ever exist an error correction code that can correct everything, right? There will be always an error model, and you will correct for that error model. For example, in standard error correction codes, the error model is local. You say my errors occur locally, and I'm gonna be interested only in one side, two side, three side errors. You will never be able to construct an error correction code that basically corrects arbitrarily non-local errors. And the idea behind that is that your error, like the likelihood of an arbitrarily non-local error is very, very small. All right, so an example is helpful here. And it also helps me introduce a notation. So this is the standard notation for error correction codes. NK double bracket. It says you're using n physical qubits to encode k logical qubits. So one standard code that's very famous, and we're going to be talking a lot about, is using 5 physical qubits to encode a single logical qubit. It's a 5-1 code. So here are 1, 2, 3, 4, 5 qubits, and you encode one logical qubit in here. This was one of the very first examples of error correction codes that was constructed. It is a stabilizer code, and written in the language of stabilizers. Here is actually a subgroup, the abelian subgroup of the Pauli group that we're interested in. We said that if you have n minus k generators, you're going to have k encoded qubits. Our k is 1, our n is 5. So I need a subgroup with an abelian subgroup with 4 generators. Here are the 4 generators of this abelian subgroup. So it's basically x, z, z, x moved around along this, in a cyclic way, along this 5 qubits. Only 4 of them are independent there is one of them because there are 5 different positions they can take. The other one is just multiplication of these guys. So it's not a generator. There are only 4 generators. This is a very famous code. It's related to what is called secret sharing and the threshold scheme, but that doesn't really matter. But the reason that we are interested in this code is that there's something very optimal about it. Well, yeah, that could be discussion for another time.
But
So,
the choice, but
yes.
the choice of these 4 generators may not be unique, right? So here probably you have chosen, you have picked up one particular choice, or this choice is unique.
Sorry, say it again.
Whether or not the choice of these 4 generators is unique.
No. Okay, very good. Of course, if you take this error correction code and apply a global unitary, right, it will change everything, but the code is still the same, right?
Mm-hmm.
So it's written in a particular basis, which is usually called computational basis. Now, what is unique about this is there is something called what is unique about, usually the notation that is used for error correction codes is a little bit more elaborate. You write it NKD. This is the largest, this is the smallest operator of this is the size of the operator of smallest support that cannot be corrected. So in this case, the code is 513, which means that any bilocal error could be corrected. Right? Any two-side error can be corrected. Now, there are other ways of encoding a single qubit in 5 qubits, but this error correction code has protection against errors of support as large as possible. There's a trade-off between how large of an error, how large of a support for an error can you tolerate and how much information you want to encode. But yeah, there's something very optimal about this. There are a bunch of inequalities for how good of an encoding could be, how tolerant it is, how much noise it can, what kind of noise it can correct, and this is pretty optimal. So usually,
sorry, I didn't completely understand. So wait, 5 qubits, you simulate 1 qubit, but that qubit can be in any state or only in the stabilizer state?
No. It could be in any state.
Oh, okay.
It could be in any state. Yeah.
Yeah, thank you.
So very good. So there is an encoding procedure, right? Every quantum error correction code is an encoder. It encodes a single qubit, so you can think of it as a circuit, which as an input, now we usually draw it in terms of tensor diagrams. As an input takes 1 qubit that I'm drawing is red. You'll see why I use this notation. And then as output comes 5 different qubits, right? So it encodes a single qubit in 5 qubits. This is like a quantum circuit, and this quantum circuit is going to be the fact that it's a stabilizer code tells you that this quantum circuit is comprised of only Clifford gates or stabilizer gates, so only C0, phase, and what was the other one? Hadamard. Right? So this gate only has these guys and nothing else. So this is a stabilizer code. You could bring this and put it as a leg and think of this whole thing as a state of 6 qubits, in which case this is also stabilizer state. We usually write this in the notation. It's a silly notation. Well, it's like an abuse of notation. We write it in this language: 0 qubits encoded in 6 qubits. But that just means that it's a state. It's basically this map could be viewed as a state on 6 qubits. All right. Are there any questions about this particular code?
Can you elaborate what do you mean by state? How do you make this logical qubit into a state?
Oh yeah, so it's just this. So let's say here is some encoding map that is an isometry that takes as an input a single qubit and gives an output a two-dimensional subspace of 2 qubits, right? How do I think of this as a state on 3 qubits? I just turn this around. This is a state of 3 qubits, and I can view this as an entangled pair. So I can play this game with arbitrary tensors, right? Did I answer the question?
I don't think I still get it. What are the first two legs that come in?
Okay, so first, is this diagram clear? So this is some isometry that acts on a single qubit and gives a state, the encoding, right? State of a two-dimensional subspace of 4 qubits.
And this state is the state of the logical qubit.
So these are logical qubits, yes.
And the same for the state on the left, right?
This is not really, this is an encoding. I mean, this is sort of like, this is what I want to simulate.
So with these 5 physical qubits, the Hilbert space is basically a tensor product of 5 states, right?
Yeah. So these guys, the I tildes. So because this was two-dimensional, right? This I's span a two-dimensional subspace. After an isometry, you end up with a two-dimensional subspace of, say, in this case, 2 to the power of 5-dimensional physical Hilbert space.
Mm-hmm.
Right? So here is what the encoding is.
Yep. Okay.
And now I can view this as in the language of tensor diagrams, we usually write it this way, which means that I can think of this as, well, I can write it formally what it means. It means that, so you have V acting on, so there are 3, I should write down the state of 3 qubits, right? V tensor identity acting on 1 and 2, and this is acting on E of 2, 3. Well, sorry, this notation might be unfamiliar, but this is what it is. But anyway, it doesn't matter. So there's a way to that way.
Okay. Yeah, I think I get it. So basically, you have physical qubits and you have a single logical qubit, and when you which is the red line, and then you kind of think of this logical qubit as just another qubit.
Yeah, exactly. So okay, maybe I should return it this way. So instead of, like you have this state, you could think of this as the following state. 1/30. This is that entangled state.
Okay.
Yeah,
Okay.
this was the easier way of writing it. Okay. Now, why did I walk you guys through this example? The reason is that the error correction codes proposed as toy models of holography are basically repeated use of repeatedly using. You get them by just like repeatedly using this code. That's all that there is. So here is the building block. This is called the pentagon code. 1 leg comes in, 5 go out. So the legs coming in are the red lines. These are bulk data. This is the bulk effective field theory. So this is the bulk, it lives in 1 higher dimension. And then there's a boundary theory that lives in 1 less dimension. So the input, so holography is understood as a map, here is understood as an encoding, as an isometry from the bulk to the boundary. So you put in, you tell me what is the matter distribution in the bulk, right? So that's some state that will describe for me what is the state of the red legs, and then pops out as a result the encoding state of some boundary theory, right? Which has a lot more legs, right? And that is sort of supposed to be the holography example. This is a toy model of holography.
But sorry, why more legs? You should have the same number of qubits. Or
No, it won't have the same number of qubits.
But-
In the continuum limit, they become infinite dimensional, all of them. So,
no, but the bulk and the boundary should be the same. Or
I mean, this is a discrete model. What do you mean they should be the same? There are, yeah, there are like, in this example, the bulk and boundary have different dimensions.
then they are not the same theory, I guess. So,
Oh yeah, they're definitely not the same theory. One of them is like free fields in ADS, right? The other theory is some strongly coupled CFT in one lower dimension.
I mean, but in holography, they should be the same theory or not.
Sorry, what do you mean by the same theory? Is
I mean, ADS n equal 4 supermid is the same as type 2B on ADS 5 cross S5.
yes, but like when you do construct the states as you're definitely not saying that semi-classical gravity and ADS is the same theory as so we are looking at the low energy sector of the superstring theory on ADS 5 cross S5, right? So we're not looking at all. So there's a semi-classical gravity in the bulk.
Yes, but okay, that's not okay. Well,
That
so-
has a notion of locality. Otherwise, in full string theory, what's the meaning of locality, right? There's no question.
Hmm.
Yeah, so this is understood as a map. This is a toy model of a map from semi-classical gravity Hilbert space to the, say, near vacuum states of the semi-classical gravity in the bulk to near vacuum states of this boundary CFT. It's a toy model, right? It's the first order, 0th order toy model that has some error correction properties that we expect from ADS CFT. But the whole point is that I'm interested in this case is that this is called the stabilizer tensor network. The reason is that when these gates are stabilizer gates, so these guys are only comprised of C0, Hadamard, and phase. That's just because of the error correction property. It comes with it. And you could, as I said, you could view this as a single state, you know, like trading the pentagon for hexagon, and that's called stabilizer tensor state. It doesn't really matter. It's just sometimes you see pictures like this in the literature, and that's basically what it is. All right, so I said all this to say that there is this simple class of states called stabilizer states that are useful and they're used to construct most of the quantum error correction codes that we know, including those that are proposed as toy models of holography. That's basically what I want to say. Now, another statement that I made, which I haven't quite backed up yet, but I'll quote a theorem, is the statement that this class of states called stabilizer states, they are easy to simulate classically. That's important. So the fact that they're quantum states is not buying us much. Another thing to know is that, well, I just claimed that the vast majority of quantum error correction codes that you know are stabilizer states, stabilizer codes. So you might tell me, oh, what about the Toric code? The Toric code is also stabilizer code. That's actually a second example in case you have that in mind. So here's the Toric code. I'll go through it very quickly. So here's the 2D lattice. On each link, you have a qubit, and the Hamiltonian has a bunch of vertex terms, and it's just minus a bunch of vertex terms minus a bunch of plaquette terms. So each vertex term is on each link of a vertex, adjacent to a vertex, you put XXX operators. And for the plaquette, this is the plaquette. Around the plaquette, you put ZZZZ. Right? This is the Hamiltonian of the Toric code. Now, the point is that for all vertices and plaquettes, these guys commute. Of course, if the vertex is here and plaquette is here, they commute. But also, if they are right on top of each other, they also commute. Can prove that. The reason is that they always overlap on 2 links. These guys also commute. You could believe me on that, but it's a 2-minute argument to convince yourself. And in summary, these vertex operators and the plaquette operators, they generate an abelian subgroup of the Pauli group, because as you see, they only involve X and Z operators, right? And this is the abelian subgroup we're talking about, and the ground states are the invariant states of this abelian subgroup. Why is that? Because we said the ground state is the state that are invariant under it. Therefore, they correspond to the eigenvalue 1 of this guy and eigenvalue 1 of this guy. That minimizes the Hamiltonian energy, minimizes the energy, right? Those are the ground states. So the Toric code and its generalizations are also all of this stabilizer codes. So the vast majority of codes that we know as topological quantum codes are also stabilizer codes. Any questions about this? There are, I should make this caveat, there are non-stabilizer codes as well, but there are very different constructions and they are not the very famous codes. Those are not the codes that you will hear about all the time. So now I want to explain, I think I have the time, why, what's good about stabilizer codes. Why do we care about stabilizer codes? The reason is something called fault tolerance. What is the idea? So the idea is that you just don't want, we want to do quantum computing. We're not interested in only storing information. We also want to process them, which means that you encode a qubit in 5 qubits, another qubit and another 5 qubits. Okay, so you have quantum memory, but that's not what we want to achieve. You also want to apply some sort of unitary, this logical gates you encoded. So physical realization of this logical gate is a 10 to 10 qubit gate, right? Because it takes as input 10 physical gates and pops out as input 10 physical gates. Now, you might worry that if an error occurs here before you acts, well, you have an error correction code, so you could correct it. But after this you acts, if this error propagates to all of these 10 guys, if the errors, the support of errors just propagate really fast, well, here you could correct local errors. But if this U makes this local in the next step, a 5 local error, then your error correction is useless. So here's when the notion, where we introduce a notion of transversal gates. Transversal gates are those gates that if you, it's a logical gate whose physical realization is, if you want to do U, you do, so you realize it in this way. You pick the first one of these guys, apply U to it. Then you pick the second one of these guys, you apply U to it. Third one of these guys, you apply U to it, and so on and so forth. Such physical realization of a logical gate ensures that your errors don't spread out of hand, right, in an uncontrolled way. And this helps because it means that you could repeatedly apply this. This is the notion of fault tolerance, is that you could apply many gates, and at the end of the day, you could run your error correction and make sure that everything is fine and correct for your errors, right? So if you don't apply transversal gates, if your errors spread in an uncontrolled way, you can't error correct after applying a bunch of gates, and you don't have what's called fault tolerance. Fault tolerance is that the fact that the combination of storage and applying gates is correctable. So fault tolerant, so we hopefully I just argued that transversal gates are one way of making sure things are fault tolerant, meaning that they could error correct after applying gates. Now here is, yes.
So could this be understood as a way to suppress information scrambling?
In a sense, I mean, scrambling of errors, right? So
right.
You want to allow your encoded interesting logical information to scramble, but you don't want the errors to randomly scramble. Yeah.
So here you essentially you have decomposed U into a few U's, right? So each time you just work on essentially part of the physical qubits. But
yeah, it's
eventually
like an architecture, right? I have to decide how to apply a logical U, right? And this is a particular architecture that is resilient against noise in the sense that it doesn't allow noise to spread fast. But I'll immediately tell you that I can't get away with this. I can't do this. So the reason is what's called the Gottesman-Neal theorem. They prove that there exists no error correction code that can transversely implement a universal set of gates. So if there's a set of gates that, well, we are interested in applying a universal set of gates to our logical qubits so that we can apply arbitrary operations. And these guys prove that there's no hope of, there's never a hope, there's no hope of ever doing that in a transverse way for every single logical gate. However, the Pauli group can be implemented transversely on any stabilizer code. In fact, this theorem shows that there's a polynomial time classical algorithm to simulate any stabilizer state. There's a leap in logic, but there's content to the theorem. So these two are equivalent statements. But I haven't explained that. So what we learned from this is that, and if I come to you and say I have a quantum computer and I have a quantum circuit that I want to implement on this quantum computer, you look at my quantum circuit and it has a bunch of gates. You want to understand how hard is this circuit, how difficult is this circuit to simulate classically, or you just want to say how quantum is this circuit. Well, you look at the circuit, you just discard all the Pauli gates out of it. You first write it in terms of a universal set of gates, which is Pauli plus T. You discard all the Paulis, you only care about T's. In fact, an n qubits quantum circuit is only as hard as the number of non-stabilizer gates it has. Or you can, if you are decomposing in terms of T's and stabilizers, the number of T's it has. So to get exponential speed up compared to classical gates, we should be looking at algorithms, only algorithms or operations that involve a polynomial number of non-stabilizer gates will ever have a hope of doing something beyond classical physics, classical computer, beyond the reach of classical computers. And okay, so this is sort of an important statement. And here's when the notion of magic comes in. Okay, I'm running really behind. Magic states are, so what you say is this, magic states are like a resource. These are non-Clifford, non-stabilizer states that you give as input next to your zero tensor n and apply Clifford gates to. Because you have a bunch of non-stabilizer states, now you could do something that goes beyond classical physics. Classical computing. So that's the terminology of magic states. So these are states that are non-stabilizer. Or I can talk about magic gates. These are gates that are non-magic, non-stabilizer. Okay. All right. So a more technical definition is this: any state that if you have an infinite supply of, so this K I can choose to be arbitrarily large, as an ancilla, I can get universal quantum computations using only Clifford gates. So here are only Clifford gates, and I introduce arbitrary copies of this particular magic, this state. Then I can get universal quantum computing, arbitrary state of the Hilbert space. This state is called magic. This is like a formal definition, a way of formalizing what I just told you, things that are beyond stabilizer states. So an example would be 0 plus e to the power I pi over 4 identity divided by square root 2, which is like, it's the same thing as applying t to 0. sorry, not zero, applying t to plus state. In fact, I can, any state, in the case of a single qubit, pure state, any state that is not an eigenstate of a Pauli is a magical state. Now, there's a huge literature out there started by Kitaev that studies what is, you know, like if I give you a density matrix, a mixed state, how much magic is there in it? And then there's something called magic state distillation, blah, 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 that we don't want to get into. But that's a huge part of when if somebody comes to you and says, gives you some sort of circuit, a huge part of saying how much non-stabilizerness is there in it involves something called magic state distillation. But that's a topic for another time. How much time do I have? I have so I got finally to the CFT part.
Yeah, we don't have like a strict time limit, but
But I don't want to bore people either.
just keep. Yeah, I don't know. I mean,
Okay.
it's up to you.
So-
I mean, it's 4 minutes before 3, but you can go
Okay.
over. Yeah.
So are there any questions about the first one? So far, all I said was that I reviewed or tried to explain in an intuitive way what magic states are, what are Clifford's or stabilizer states, or otherwise known as Clifford states and stabilizer gates and their connection to error correction.
Nima, maybe you will talk about this in CFT section, but can you say something about mirror network or MPS?
Oh, absolutely. Yeah, that's where I'm going.
Okay, thanks.
Sure. But I won't say something satisfactory to your satisfaction, meaning that this was first studied in 2020, shockingly, and was published in 2021. This is the paper I cited at the beginning. And the study of the way these guys study it is like very, very simple arguments. Like I think there's room for a lot of work. There is very little known. So there is a discussion on Mera that I'm more than happy to discuss offline. I don't think I'll have time to go through it, but anyway. So here's the title of this paper: Conformal field theories are magical. So let's just review. Stabilizer states show up in topological order, quantum error correction, and quantum gravity, toy models of quantum gravity, holography. They contain entanglement, but no magic. Said differently, they're easy to prepare classically. Now, we would like to know how magical are the ground states of CFTs, conformal field theories, or ground states of quantum field theories. So we need a measure of magic, which measures the degree to which state cannot be approximated using Clifford gates or stabilizer gates. Clifford gates and stabilizer gates are the same things, right? Like it's just different terminology for the same thing. C0, phase, and Hahnemann. The measure has a weird name, mana. And what these guys do in this paper is that they consider the Z3 state, the 3-state Potts model at the critical point and show it has large mana. And they also show that this magic, this is a measure of mana, is a measure of magic, is or non-stabilizerness is present at all scales. So, and also another statement that these guys make is that magic is essential for holography. The reason being that stabilizer states are over-constrained to be realistic. But in the remaining time, I want to go through this pretty quickly. So these are the statements. Maybe I should pause. Is it clear what these guys try to establish? So they take Z3 Potts model and do numerical calculation, and they calculate a particular measure of magic, non-stabilizerness. I dislike the name magic, but anyway. And they show that this measure is maximized at the critical point. And when it's where it's maximized at the critical point, it's present at all scales. The same way, so we usually say that ground states of CFTs are highly entangled. So you might think that, oh, that means that the ground states of CFTs are very quantum mechanical. But unless we show that they have magic, we haven't proven that they could not be efficiently simulated on a classical computer. So these guys established that they have a lot of magic, which means that they're hard to simulate using classical computers. All right, maybe I don't want to go through this. So no, let me just go through this very fast. So I described the Pauli group and Clifford group for qubits. Of course, it generalizes to Q-level systems. So because I'm talking about Z3 Potts model, I want a 3-level quantum system. So there's a generalization of the Z and X operator. And there's a generalization of the Pauli group. This is like shift, this is clock. In condensed matter theory, that's what they're called. And these guys, if you just multiply them, the same way that Z and X generate the whole Pauli group, these guys generate the generalized Pauli group. And then there's an n qubit version of it, which is you just take these generalized Pauli operators and tensor them together. You get a n qubit, sorry, n qubit Pauli, generalized Pauli group. Of course, the definition of the generalized Clifford group is the same. These are the set of unitaries that preserve the Pauli strings, generalized Pauli strings, up to a phase. I didn't mention the phase before. This is an important thing that's considered here. This phase has to do with that plus minus one that I put in the definition of Pauli group. But anyway, let's not worry about that. The point is that this Clifford group, the same way that in the case of qubits, it was generated using Hadamard, phase and phase operator and C0, is generated using a generalization of the Hadamard operator that looks like this. Remember that Hadamard was just 1, 1 minus 1, 1. A generalization of phase operator, if you remember, this was the phase operator. This is the generalization of it. Omega is just e to the power of 2 pi I over q. Q is the level, right? So if q is 2, this becomes 1 pi. And then there's a generalization of C0, which is this guy. All right, so this gives you a notion of generalized Clifford group. Generalized Clifford states or stabilizer states are just take 0, 0s and apply these guys to it. And then this is non-universal. You need a generalized T operation, which is something like this. It's just a diagonal. Remember the T operation was just 1 e to the power of I pi over 4. This is a 3-level version of it, where sigma, where C is just e to the power of 2 pi I over 3. All right. So the magic monotone is any function that's non-increasing under Clifford gates. All right, I'm just gonna jump to, I'm gonna skip the definition of magic monotone, mana. I'm more than happy to talk about it offline, but there is a measure that we call M, Curly M of rho, that's called mana, and it measures, I can explain why, but it measures magic, non-stabilizerness. Which means what? Which means that this measure is 0 if and only if the state is a stabilizer. There's a theorem called discrete Hodson theorem that makes sure that this measure defined this way, I didn't tell you the definition, is 0 if and only if the state is a stabilizer and the measure is positive. Okay, so I'll jump over that. And also, this mana has been used as a measure of the difficulty of the sign problem in classical Monte Carlo simulations. This should be an indication of the quantumness of it, why it's actually telling you about quantumness. All right, that's good. Let's just go to the Potts model. So here's Q3 state vector Potts model. Here is the Hamiltonian minus sine theta. Oops, sorry. This is 1D Potts model, right? ZJ dagger, ZJ plus 1. These are the clock operators. And then this is XJ dagger, XJ. These are the shift operators. This model is critical at theta equal pi over 4. At the critical point, you get the Potts CFD, which has central charge 4 over 5. So it's a 2D CFD with central charge 4 over 5. it's the simplest, it's one of the simplest CFDs that we know. Actually, it is the simplest CFD that we know that doesn't have a factorized partition function. But anyway, mana. So these guys, what they do is that they numerically study mana in this system, and they find that it's maximized at the critical point, and at theta equals 0 and pi over 2, the ground states are stabilizer, therefore mana is 0. So here's what the diagram looks like. It just goes up at theta equal pi over 4 is maximized and comes down. This black curve is when they did the simulation for a smaller number of qubits. So they got a curve that was nicer, but it's not peaked at the center. So these curves are, they push the numerics for a larger n. All right. Okay, so here I'm just gonna summarize the observations. They look at mana density, which is the reduced density matrix of L sites divided by L. And they meant that they observed that at the critical point, this is an order 1 fraction of its maximum value allowed possible. So in any state in quantum mechanics, we'll have mana at most 1/2 ln of 3 times L. We're dividing by L. This is a qubit system, subsystem of size L, right? And they find that numerically, they find that mana is always order 1 fraction of this. And also they observe that mana is present at all scales. What does it mean? It means that here is their spin chain or Q-trick chain. They consider mana for bipartite density matrix on site I and J, and then they separate I and J. And they observe that mana falls off polynomially with distance. So interestingly, it just means that mana is present at all scales. So the reduced density matrix of a bipartite system in the ground state is classically hard to simulate, even though you pull these guys apart for large distances, right? Like as you pull them further and further apart, the difficulty falls off only polynomially. Okay, so that's one work. There's another work that, yeah.
Does this conclusion hold only at the critical point, or this is
only at the
valid
critical point,
for
yes.
any theta? Okay.
No, only at the critical point.
Okay.
The you mean the parallel fall-off?
Yes, I'm talking
Yes.
about the parallel.
The parallel fall-off is only observed at the critical point. Yes.
Thanks.
So it means that mana cannot be removed by local unitaries. So that's what it means to say that it's present in all scales. So hence the funky title of their paper, CFDs are magical. You might ask, why didn't they study C=½ Ising model? I don't know, but I can tell you that there is another paper that appeared this year, very recently, that claims that the ground state of C=½ Ising model also has a lot of magic, but they use a different measure of magic. That's not mana. And I have not studied this paper in detail, so I will not stand behind it. But yeah, there are claims out there that are very recent about an integrable model, C=½ Ising, right?
Actually, yeah, I have a kind of a related question. So
Yes.
how about C=1 if you just have, let's say, free fermion CFD or free boson?
I think it's a very good question, and oddly, I could not find literature on this. You see how recent this is, right? This is just like very recent.
Yep. Okay.
So I was surprised. I wanted to email Brian and ask him why did he start with 3-state Potts model. I didn't have time to do it, but it will be interesting for me to hear. I think he has some intuition that it's not articulated. It's not been articulated in the paper.
I'm not sure I understand, if I may. Ising, C=½ Ising is Majorana fermion.
Yeah.
So free Majorana fermion.
Yes.
So C1, I think you mentioned free Dirac fermion would be 2 Majoranas.
Yes. Yeah.
If one Majorana has a lot of magic, my inclination would be to think that 2 Majoranas will have also a lot of it.
Yeah. Maybe my confusion is that I would have thought that the free fermion
Absolutely.
has no magic at all.
I agree with you.
Because
When I
it's
saw
the
this,
trivial thing,
I was
so.
thinking exactly along the same lines. But when I saw this last reference that Nima included, indeed, it is, guess what they call deserves further study.
But like it is. I mean, free fermions has a lot of entanglement at all scales, right?
Sure. But you told us entanglement is one thing and magic is a different thing.
Exactly. So it is
Right.
kind of surprising to me as well that
Correct.
this is sort of
Right.
present at all scales. To the authors, it was unclear that they're going to find this. So they make a big deal out of this, actually. That it was unclear that they're going to find that magic is present at all scales. Now, I have to say that they have so the ground states of a two-dimensional CFD, one of the ways that we think about this entanglement structure or its preparation is in the language of Mera tensor networks, right? I told you that magic, actually mana, provides a lower bound on the number of T gates that is used in the preparation circuit. So you could ask how much T gates do you need to does your Mera use? And they use some like counting arguments. They're very crude counting arguments to get some estimate of it, and they try to sort of qualitatively explain this behavior. Now, I think there's plenty of room for further investigations, because if you look at their arguments, literally counting argument, they say that, oh, let's assume every gate adds 0.3 value of mana. And like, why? We don't really know. It's just to just add them up. But anyway, I think there's a lot of room for future work. Let me finish by a slide that has to do with holography and quantum field theory. I found they make these, so they say their results suggest the following ideas or thoughts, which I sort of sympathize with. So first of all, they say magic distillation, or the preparing magical gates, will dominate the cost of preparing ground states of quantum field theory. So there's a literature out there it was started by Preskill and friends, and it has exploded into like a whole set of various different discussions and work. And these guys suggest that if you want to be careful with the amount of so it's all about simulating quantum field theory on a quantum computer versus a classical computer, right? So these guys say that the important thing that will make it hard for you to simulate the ground states of quantum field theory on a classical system is going to be basically the number of T gates that you need, the non-Clifford gates that you need. And it comes from the fact that mana is extensive in subsystem size. This is the statement that I made, that mana of rho L over L was order 1, right? Okay, this is sort of interesting actually to think about. Maybe I should say this again. Well, in entanglement, you have log L behavior. Here you seem to get an extensive behavior, and I do not understand this. It is sort of interesting to look into this deeper, but they also say that this work suggests that stabilizer tensor networks and holography could be improved. They have undesirable features. They have flat spectrum that CFDs do not, and we do not expect in gravity. A flat spectrum doesn't mean much to you. Just let me just say that they have undesirable features like correlation functions that are unrealistic. And they say we could improve on our holographic tensor network model, make them more realistic if in these tensors we just squeeze in some T's in there. So we have to think a little bit harder about what it means to change this. But they suggest if you allow for this gate to have some T's, some T gates, then so there's a compromise. As you make this go away from the stabilizer code, the error correction code in holography is going to be an approximate error correction code. So you're going to introduce, it's not going to be a perfect error correction code, but you need that approximateness, you need that fudge factor to allow for correlations, to allow for the model to be realistic. Anyway, so this is where I want to end this, and let me just summarize at the beginning. So what did we discuss? We introduced or reviewed stabilizer states. These are the class of entangled states that are easy to simulate classically. They play an important role in error correction code, topological quantum computing, and tensor network model of holography. Magic states are non-stabilizer states, and turns out that ground states of CFDs have plenty of magic at all scales, an extensive amount of magic, which surprises me. And then the proposal is that we should add magic gates to holographic tensor networks to make them more realistic. Thank you so much.
Okay, thank you.
Nima, I have a question related to the last part. So
Yeah.
we discussed free fermions just some minutes ago. They have a holographic dual, which is one of higher spin gravities in ADS3. So I'm talking about 1+1 dimensional fermions and the holographic dual in terms of higher spin. So is this somehow related to the last part of your talk, that if holography sort of, maybe I'm misinterpreting, but if holography sort of requires magic?
Okay, so now okay, so I would say what we mean by holography are we might mean different things by holography.
Right, exactly.
When you say free fermion or holographic are dual to the tensionless limit of string theory,
correct,
the Vasilia theory, that theory is highly non-local in the bulk.
Right.
Whereas you will only get so in the low energy, it will not reduce to Einstein's equations. You'll have these higher spin modes that will survive in low energy, right? This model of holography, this toy model of holography is constructed based on the idea of locality. So it will only be a realistic model of these tensor network diagrams, will only be realistic models of holographic theories that in the low energy reduce to something local, like Einstein's gravity. So, and with a large gap that lifts all the stringy modes. Right?
No, I understand that. So you're saying that we're talking about different holographies in a sense. The one that has large gap for the operators beyond few lower dimension ones. However, the three-dimensional high spin gravity has Einstein gravity as consistent truncation, if I remember those things correctly. So I can imagine limits in which, although I understand that higher spin story has non-locality in it, I can imagine limits where locality is in a certain sense
that's a very good question.
Preserved.
It is a very good question. It's true that if you truncate three-dimensional bulk higher spin, you could truncate the three-dimensional higher spin only to spin 2. And I think there's a dual that was suggested by the ETH group. This is some sort of a
the story is that the dual that they suggested it contains scalar matter. In fact, this is one of Vasiliev theories, which contains, in addition to higher spin field, scalar matter, which is spin 0 matter.
Oh, I see. I see.
In the bulk, and if you start giving expectation values to scalars and such, then this property of consistent truncation is lost. And in the boundary theory, that corresponds to giving fermions a mass. So this is some kind of deviation from criticality. I'm not sure I'm making sense here, so maybe I should stop. But
no, but I would just say one thing, which is, as far as I know, even though you could truncate those theories to Einstein's equations, you will not have black hole. It will not be really a theory of gravity. You will not have black holes in the standard sense of it, because the notion of event horizon is gauge dependent.
but again, if you only work at BTZ, look at BTZ black hole after you have truncated, that shouldn't show up. What you say is when you start adding, let's call them chemical potentials for spin, for high spin fields in the boundary, then you start developing black holes which have, let's call them funny properties along the lines of what you were saying. Anyway, one just needs to look more carefully into when consistent truncations are possible and when they are not. What are the conditions?
Carefully about it, and I do not know much. It would be interesting to look at it because, like, I think it's an exact duality that is under control, right? As
Right, right.
opposed to
Well,
the
in the control modular comments that you made a minute ago, that these higher spin theories, they are non-local, for instance, and they are not conventional gravity. So that.
So I would say one thing, which is, so I don't know the answer to what you said, and I think it's a very, very good research project to pursue. But I would say one thing, which is when we studied error correction, so we studied error correction and these type of like mirror type error correction, and we tried to look into what makes it holographic. There were two different ingredients that went into it. One of them was large N, and the other one was large gap. And we were playing different roles in terms of error correction. So the models that you're talking about are definitely large N. So they have the large N error correction built in. And I don't really know how far it gets you.
Right. No, that's the question. Exactly. That is exactly the question. Yes.
I think it's something to investigate. Within Mira class, we could separate that role of large N and large gap. But I think these models are potentially, we're actually looking at the same problem in ON right now.
Interestingly then, Akhil and I kind of wrote a paper on free fermions, and what we have found that if you look at computation of entanglement entropy, we didn't know about magic. Well, we did what we knew. Entanglement entropy, then even though the dual is higher spin gravity, in certain limits, you can still use Ryuta-Kayanagi formula.
That's interesting.
As if the gravity were Einstein gravity.
No, this is a truncated theory.
Nope, this is the whole thing.
Oh, okay.
It truncates itself automatically, in a sense. In other words, you can go to a limit where computation of entanglement entropy in theory of free fermions, massive free fermions, can be done using Ryuta-Kayanagi formula as if all those higher spins did not exist.
That is very curious.
Even though the higher spin fields are actually there. Scalars will source higher spin fields. Well, I mean, I don't want to take everyone's time with that. We can discuss it. We sort of understand the reason. And it's related to Lefkowitz-Maldacena type of constructions for holographic computation of entanglement entropy. That in a sense, you can extract entanglement entropy from an action-like quantity, which is like Gibbons-Hawking type of formula for ordinary, for computing on ordinary entropy. Gibbons-Hawking tell you that you can extract that from an action principle to compute action of your space-time and do things to it that, that they do. And there are similar statements, as I quoted the paper, the work of Lefkowitz-Maldacena, where they do the same, well, not the same, but parallel for entanglement entropy. And because of that, the statements, they are non-obvious, at least they weren't obvious to me, but they not entirely bizarre in a sense of that, when you kind of think about it. Anyway, as I said, don't want to take everyone's time.
Thanks so much for the comment. I think it's definitely something that we should look into. We've just started this. It's kind of bizarre how new this whole field is.
Right. ON models may be the same way because they share many properties with this free fermion duality, the ON models have similar properties in a sense that they are dual to these high spin fields, again, as you mentioned. Right. I don't know, maybe we should continue this sort of investigation of these issues, because I think this is kind of promising on various fronts.
For me, as far as I'm concerned, I'm on a mission to improve the tensor network models of holography. That's how I stumbled in this. Like, that's on my agenda. It's sort of like high priority on my agenda. So I think it's a very. I would be definitely interested in pushing this further. So we should talk more offline.
Right.
Okay, I'm gonna stop recording first.